So again, we are focused back on the matrix force method, and today we are going to discuss another example on a frame where the supports are a spring, right? So let me share. So you can see this example from this Garley-Neville's structural analysis book. So this is pretty good, pretty advanced structural analysis book that you can refer for as a beginner, right? So let me get back to the problem straightforward. So use the force method to find the bending moments at the supports of a continuous beam on elastic spring support, right? So the beam has a constant fracture rigidity EI, and the stiffness of the elastic supports K is L over EI, right? So right. So you have been given uh, that the K is 20 EI over L squared, right? What is this K actually? So you know that F equals Kx, right? So actually what is K? K means, so just think of, just take this as one. So unit displacement. So force is equal to stiffness into displacement, right? So that means F is equal to K, right? So that actually means force, okay, force given for a unit displacement, right? To obtain a unit displacement, how much force do you require? That's stiffness, right? Force per a unit displacement, right? So you can actually so the inverse of stiffness is the flexibility always, right? So that is going to be the displacement occurs for a unit force, right? So that is flexibility. Okay, so I can go with now. So they are telling me this is your bridge, and here you have roller supports, and pretty much here you don't have any horizontal loading, so you only have, so these are kind of rigid supports, but this spring can deform, right? So actually you only have VA here, VB here, okay. Sorry, this is VD, right? This is VD, right? A, B, C, and D. So you have altogether Q per unit length, right? And your length is L, L, and L. So pretty much this is a symmetric structure, so that you can take VA equals to VB as well, right? No problem. But to be honest, we will take this as a redundant for now, right? So you have here one unknown, and you have a force in this spring. So this is just a spring, so it can take axial loading, right? So one force, so here also one force, and here as well. So you have altogether four unknowns, right? But since we already have uh, two equations also, because we cannot take horizontal equilibrium equations if we do not consider the horizontal reactions, because those are zero. Why? We don't have any horizontal force, right, in the structure, so those are zero. That means we cannot use that equations as well. So we have altogether statical indeterminacy, four unknowns, and two reactions. Just forget about for this now. Just consider a common case, right? So in that case, statical indeterminacy is 2, right? So that means you have to remove two redundants, right? And so I'm completing this for a common case, so that even if it is not symmetric, you can work it out in the same way, right? So here, either I need to remove two redundants, right? So how I'm going to do that is either I can form two hinges, or else I can remove two redundants. Form, okay, form, introduce. Not from, it is form, okay? So in such case, my first method will be introducing a hinge, right? Introducing a hinge so that I know at A and D, I don't have any bending moment. So eventually that's going to be zero. So I can form a hinge at B and C, right? Once you form B and C a hinge, the bending moment at B and C for each member is going to be zero. So your spring doesn't take any bending, right? So please be remember. So the stiffness is given on the axial direction, right? So if you apply an axial force, your spring is like that. Think about just a spring, right? If it is given the axial stiffness, it has not given how much will the bending. So if you apply a bending, so it will bend, right? So that lateral stiffness or any other thing is not given. So we apply only an axial force in that spring, right? So if you apply a hinge, so here to here, the bending moment will be zero, right? Yeah, so the bending moment will be whatever zero. It's going to be zero, right? At the hinge. Okay. So one thing you can do is, so we are working on the force method, right? If you are working under the force method, what you need to do is, uh, so we removed actually the bending moment. How? There was a bending moment of, if you apply at draw the bending moment curve, that would be like this. So by introducing a hinge, you change the bending moment curve like this. What did you do? Here it's zero still. Here also absolutely it's changing, but we are only worried about the joints, right? Because that's what we need to solve at the joints. So here you didn't change. That's okay. But here it was initially some value, then it's 0. So you bring it to 0. So you make the bending moment 0, right? So you make the bending moment 0 such that it is no longer your original structure, right? So we can go ahead and this is our primary structure, right? So please, uh, yes, I can draw it here. So this is my original structure. It's just like we worked out in the previous videos. So there were the fundamentals of force method. So in the force method, we consider the compatibility, shape of the structure, right? So here we actually make the redundance at the bending moment, right? The thing we need to find. So we don't need to form many actions matrix, right? Because we need to find MB and NC, we took the redundance as MB and NC, right? So the moment we find the reduction, that's we are done, right? And we can go ahead. Wait a minute. So I was trying to tell you is, yes, the shape of the structure, compatibility, right? So we are checking the joints, the compatibility, right? So actually, it is a continuous beam. So you know that we did it in the previous video. If it is continuous beam, you know the relative rotation of this beam is 0, right? Why we are taking the rotations? Because we are removing bending moments, right? So the displacements corresponding to a bending moment is actually a rotation, right? So we use displacement. So there are two kinds of displacement. Actually, a linear force is corresponds to a linear displacement delta, right? In this way, right? A bending moment corresponds to theta, a rotation. So we both call this translation. This is a rotation. Sometimes we call it displacement. Sometimes we call this also a displacement, even though it is a rotation, right? So we actually we use force for moment and forces, right? It's a common term in force method. So don't worry if somebody tells you if this is the force matrix and they insert a moment. So this is also a force, a redundant that we need to find, right? So these are common terms used in the force method as well as the displacement method. So force is actually used for both forces and moments, and the displacement is actually used for both linear displacement, in other terms translations, and as well as the rotations, right? So it's a continuous beam, so that you know. So I'll zoom this part. So if it bends, it will be like this. So compared to this part, the other part has not relatively rotated. Okay, the relative rotation is 0, right? But what happens if you introduce a hinge? You remember, I've shown you, right, in the previous video. I'll show you again. I'll show you again. I think I miss that? So you can see if you apply a continuous beam, so you can see the beam is always straight, right? So here, not the rotation, relative rotation, right? Compared to that part, the right end, the right part, right hand side part, how much it is relatively moved. You know, it is in the same straight line, right? So that means the relative rotation is still zero if it is continuous. But if you provide a hinge so that it can move relatively, right? Can you see there's a relative rotation? It no longer in the same line, right? So there's a relative rotation, right? So if you are hinge, the bending moment is zero. How it is allowed to rotate, right? So get the concept at the continuous, this kind of support, the sigma m is zero, but here the each bending moment is zero, right? And yes, we are good to go. Like this. Yes, relative rotation is zero, and I can go ahead and mark the primary structure. This is my primary structure. Right. So I'm forming a hinge. P and C, so that it will, so you remember, it will deflect individually, right? Each part, because it's like now separated, right? So each part now you can separate it from the hinge, right? Right. But we need the force on the spring, right? To I will tell you why. So now you have actually displaced this beam relatively, right? This is also, so it would be symmetric, right? So the W and all thing L, right? So if I call this alpha, this is going to be alpha, this is going to be alpha, this, and this, everything alpha, right? So your relative rotation, right? So I'm taking bending moment, so I will take this bending moment and clockwise positive, okay? If I know this is already equal to this bending moment, right? And you know uh, this is zero because at the primary structure there's a hinge. So if I want to find MB and MC in the original structure, what do I need is I can find either one of them. So I can find this, and I can find this both. This is equal to the left side part. This is equal to the left side part, and the direction is opposite. That's it, right? So I will take clockwise positive. Okay. And yes, here you have MB and MC, right? Those are the redundants, right? Here you know those are zero. So it doesn't matter. So, but we are working with the compatibility. So we need the displacements, right? So here. So actually the displacement here, the relative displacement, right? You remember? So we are worrying now about the relative rotation and the relative displacement. Why we are forming a hinge to form the primary structure, right? So how did we change from the initial one? Initial one, there was no relative rotation, but introducing a hinge, there were a relative rotation. So we need to account that simply, right? So our force method is basically based on the compatibility, that means the shape of the original structure, and we change the original shape by introducing a hinge. How? We introduce a relative rotation to the system, and we should consider that finally, right? And this is going to be alpha. So your relative rotation is going to be, if you extend this tangent, so this is going to be alpha, is going to be alpha. Similarly here as well, because I need this part, so compared to this part has moved clockwise direction, that is 2 alpha, right? Compared to this part has moved clockwise 2 alpha, right? So relative rotation, right? The angle between the initial and the next half, right? Compared to this location, this part, how much the next part has moved? It has moved in clockwise direction 2 alpha. Compared to this, okay, compared to always this, right? Why? Because we are worrying on this part, right? And yes, it is still due to the external loading. So what happens when the load is applied? The springs is going to settle, right? So finally your beam will look like this actually if it is loaded. Right? So this spring is going to, so this is going to be a straight line. Why? The system is symmetric, right? So compared to this, so because why we are considering that is to, we can have another rotation due to the displacement of these springs. So it was initial here, right? So now our displacement has gone down. So sorry, spring has gone down a delta. A delta, because why? Symmetric, right? Since symmetric, this remains a straight line. Okay. So we need to find the force on the spring so that we can find delta, right? So to find delta, I can form another beta, right? So this is L. So I can write delta is delta over L is tan theta. Sorry, tan beta. Since beta are small, so I'm exaggerating the displacement. So usually these are very small, okay? So for your convenience, so these are small displacements. So tan beta is equal to d beta approximately, right? So what happens here is I need to find what is delta, right? Okay. So first I need to find delta. So delta is going to be, so F into F over K, right? Since that is a spring, F equals Kx. So now I need to find F. So what is F? So here the reaction is, so since these are separated, since this is going to be WL over 2, this is going to be WL over 2. So if these are the reaction on the beam, right? if these are the reactions on the beam, here the summation is WL, the reaction on the beam, right? So the force on the spring is in the other way around. Force on the beam is exactly similar to this and the opposite direction. Okay, so that means this beam is going to press the spring and the spring will give you an upward reaction to resist that deformation. But since the spring's stiffness is finite, so it will have a relatively considerable displacement. What happens? Your stiffness is infinite. This is going to infinity, right? This is going to infinity, so that your delta becomes almost 0, so that it will act as a just pin support, right? Where it doesn't show any displacement and it remains as it is due to infinite stiffness. So everything depends on the stiffness, right? And so we can find F over K. So F is the force on the spring is WL, and K was 20 EI. This was WL. So this is simple L. So the summation of both two at the P, okay, that's going to be WL plus W. So WL by 2 plus WL by 2 going to be WL, okay, into L cube. So that's going to be WL4 over 20 EI, right? So we need to find actually beta. Why? Compared to this part, how much this beam has rotated, that part, right? So that's going to be anti-clockwise alpha, sorry, beta, right? Anti-clockwise beta, right? So beta is going to be delta over L. So delta needs to be divided by L. So that's going to be beta relative rotation. So WL cube over 20 EI. So that's done, right? So once I found that, I can go and write. So this is in clockwise direction. This is in anti-clockwise direction. So your D1 is going to be the displacement at the first coordinate of the primary structure, actually the relative rotation. So that's going to be 2 alpha minus beta, right? So alpha you need to find. So if you apply W like this, what will be alpha? So we can go for the appendix. And it's going to be, if you apply W, so you can see, if you apply W, so you need to find F5 or either F4. So that's going to be QL cube over 24 EI, right? So that's going to be QL cube over 24 EI, and it's going to be multiplied by 2, right? So my Q is actually, I have taken it as W. Okay, sorry about that. I will take this as W. Okay, so So alpha was QL cube over 20 QL cube over 24 EI, and when it is multiplied by 2, it's going to be WL cube over 12 EI. And the beta is going to be, why negative? It is in anti-clockwise direction. Okay, so you should remove that. So it's clockwise 2 alpha, and due to the support settlement, anti-clockwise beta, right? So the total rotation is 2 alpha minus beta, so that's going to be 20. Right. So when you so you have 60 EI, 5 and 3. This is going to be 2, 3 and 5, 2 W's L squared. So since this is symmetric, D1 is equal to D2 W L cube over 30 EI. So I'm cancelling the 2 from numerator and denominator. It is in clockwise direction, right? So D2 means, again, you can take 2 alpha from here and compare to this part has moved beta in anti-clockwise direction. Again, that's going to be 2 alpha minus beta. Again, the same thing, right? So our first step is done. Primary structure is done, right? So now I need to apply unit redundant, right? Unit force to each structure, right? Primary structure without any loading, right? So this is with loading. Now need not to consider the loading, right? So if I apply, so here's a hinge. Right? So if you apply a unit rotation and you are going to apply it at B, so we reduce the either way bending moment to 0. So we need to apply either way. So here clockwise positive, right? Remember, for that part clockwise positive, because so in that case this is going to be anti-clockwise for this location, right? This is our first coordinate. Here we can, for this part we consider clockwise positive, right? That's why we need to add a clockwise here to balance that. Actually at a joint you need to, it should be equal and opposite. That's why we add the other way around, right? If you add a bending moment like this, so it is a unit bending moment, right? Not a unit rotation. Theta is not 0, but the M is 0. So this is going to be like this. This is going to deflect like this. This part has not any effect, right? So if you apply a unit moment like this, you can just take bending moment about this point. So you can separate from the hinge and take bending moment. So here, if you say VA, right, VA dash, right? So VA dash into, so I'm taking bending moment about this point, VA dash into this length L, minus, this is in the other way, minus 1 is equal to 0. A dash is 1 over L, right? So you can just write this is 1 over L. So considering the vertical force equilibrium, we don't have any vertical loading because this is the redundant applying occasion. So primary structure, we had the loading. Here we do not have anything. We apply just the unit forces at the coordinates we have, right? So 1 over L. So this should be then minus 1 over L. So this is symmetric, right? So this is going to be again 1 over L. If you consider bending moment about this point for this beam, so this is going to be 1 over L, and this is going to be minus 1 over L, right? So this part has no issues. So that's going to be 0. That's going to be 0. So the total at B is going to be 1 over L, total at C, and total at B is going to be minus 2 over L, right? Total force, total reaction, right? So this is the B reaction on the beam, right? So in such case, so first you need to identify the relative rotation, right? So the relative rotation should be, so this is, if this is alpha, right? This is beta, I would say, because those are not symmetric, because the moment is applied at a corner, right? This is alpha, right? So the relative rotation is going to be, this is also alpha. If you extend this compared to this part has moved in clockwise direction. So the relative rotation is going to be 2 alpha, right? So due to the applied force, right? So now our force, so the reaction on the beam is minus 2L. So that means the reaction is, so we consider the upward forces positive and clockwise positive, right? So you can just take so if it is negative, so that means it's the reaction on the beam is on the downward side, right? So that means the force on the spring is in the upward side, upward direction, right? So the reaction, so this is the beam, the reaction on the beam is on downward side, and the force on the spring is in the upward. So it try to pull the spring, right? It try to pull the spring, and the spring reacts and keep the beam it in original position. How the beam try to, sorry, the spring try to uh, pull the beam in downward direction. So that's why the reaction on the beam is on the down. So the beam try to pull the spring in upward direction, right? So the here, okay, so you can see here, so the reaction on the beam is upward size, upward direction. So that means the reaction on the spring is in the negative side, right? So here the spring pushes the beam, and the beam pushes the spring as well in the other way, right? So this is the reaction on the spring. So this is positive, but this is negative, right? So we have to apply 2 over L force and 1 over L force. So this is our initial position, right? So here you have the spring, right? So you have a spring. So you try to push. So the force diagram is you push it how much? So you push it in the upward direction. So it will have upward deflection, right? So here you push it in the downward direction. So it will have a contraction. So the spring here will extend, right? Extend its length, right? Even beyond the beam, we don't know. And spring here will contract its length, right? It will be here something. This point will actually lie now here. This point will actually lie here after extending, right? We don't know what is that extension. What we know is this, right? You can take this as alpha. You can take this as beta. You can take this as gamma. Again, I need, so this would be alpha. So you extend this part, right? This is not equal, this slope is not equal to this. Okay, so I need to find what is alpha, beta, and gamma so that I can find the relative displacement. Here the relative displacement is compared to this part has moved clockwise direction, that's alpha plus beta, right? Compared to this part, this is gamma, this is beta, and this is gamma. So compared to this part, right, this is the original beam part, this part has moved in anti-clockwise direction, that is negative gamma plus beta. Why negative? It's in the anti-clockwise direction, so we need to find gamma, beta, and alpha. So alpha you can find, so if you say this is delta 1, alpha is delta 1 over L. Just consider the whole triangle. Let's call this delta 2. So delta beta is from this beta, you can write. So these theta are very small. I'm exaggerating the diagrams over L. So this height over L, right? You can't take just this height because you don't know this length, but you know this length, overall length, and the overall displacement. So that's delta plus delta 2 over total length L. This length you don't know, okay? And this length you can find gamma. That's going to be delta 2 over L. This height is delta 2, length is L, right? So how to find delta? Delta 1 is equal to F1 over K. Delta 2 is equal to F2 over K. Why? The spring F equals Kx, right? So your force is 2 over L. So F1 is going to be 2 over L divided by 20 EI over L cube. That's going to be delta 1, right? So is that stiffness? Yes. So your delta 2, so don't worry on the negative sign. Why? We have taken the correct displacement direction, okay? So that's going to be 1 over L okay. So there's going to be 1. So it's going to be L squared over sorry, L squared over 10 EI, and this is going to be L squared over 20 EI, right? So if you just plug these values here, so this is going to be delta 1 over L, right? So it's going to be L over 10 EI. Where am I wrong? I think, right? So the force is this. Okay. I think correct. I L over 10 EI. So here delta 1 plus delta 2 is going to be 20, 30. So it's 20 over 3, right? So it's going to be 3L over 20 EI. So this is going to be L over 20 EI. So here the relative rotation is 2 alpha plus beta. So this alpha and this alpha are not equal. Okay. So you have to be careful on that, right? So this alpha, I would say this. I would say this is alpha dash. Alpha dash, okay. Alpha dash, and beta dash. Okay. These alpha are not different. So these alpha for a unit force, right? This is for the reaction and spring, right? So we need to find this alpha plus beta here minus gamma plus beta, right? So alpha plus beta is going to be how much? So that's going to be anyway 5L over, because 20L, this 2L over 20 EI. So it's 5L over 20 EI. So that's going to be L over 4 EI, right? And gamma plus beta going to be 4L over 20 EI. So that's going to be 1 over 5 EI. L over 5 EI. Why negative? Because this is in the anti-clockwise direction. This is clockwise, okay? So you need to take, it's for here 2 alpha. For here, the relative rotation is compared to this part. This part has moved. This part has moved compared to this in clockwise direction beta dash. So here it's going to be beta dash clockwise. So the total is 2 alpha minus, sorry, plus L over 4 EI and beta dash minus 5 EI. So actually beta dash plus this rotation, right? Beta dash plus this rotation, right? That is due to the spring settlement. This is due to applied redundant, right? So there are two things happens once you add a force. So just compare it to just pin support. If you pin support, you will have only this 2 alpha, right? but now it's the spring, so that the spring's going to deflect as well. So your beam will have another rotation due to that. So we need to consider it the same step, but within the same step we have two another steps, right, to cause it by the so we need to find alpha and beta, right? So if you just go into the appendix, right, so if you apply a bending moment, so like here the pins, so your f1, the rotation, always we are applying a moment, so the corresponding displacement is actually a rotation, right? So if you apply a unit bending moment, the f1 is going to be uh, L over 3 EI. Why? M is 1, right? So the remote end, the other end, it's going to be L over 6 EI, right? So this is going to be L over 3 EI, and that's going to be L over 6 EI, right? So the alpha is L over 3 EI, and it's going to be 2 L over 3 EI. So that's going to be 2 alpha plus L over 4 EI, right? So that is the flexibility, right? We are applying a unit force and take the displacement. So that's going to be 1 over k, the displacement. So that's going to be 1 over stiffness, that is flexibility, right? So that's why f at first coordinate, due to the redundant is also at first coordinate, right? So that's going to be 2 alpha dash plus L over 4 EI, right? So your 2 alpha was L over 3 EI into 2 L over 3 EI plus L over 4 EI. So that's going to be 2 LEI, okay, 4, 8, and 3, 11 L over 2 LEI. Is it correct? So F11 is okay, right? So F22, the other coefficient F at the second coordinate, due to the load at still the first redundant coordinate, right? So that's going to be beta, that's clockwise direction, minus gamma plus beta. So that means plus this value, right? Beta was L over 6 EI. You remember remote in the far end of the appendix, L over 6 EI. It was ML over 6 EI. So we are applying a unit moment. So M is 1 minus the value was L over 6 5 EI, because this is the value we have to add minus gamma plus beta. Okay. So we need not to subtract because it's with the minus. So we can just add it, because gamma plus beta is a positive value, minus gamma plus beta is a negative value, right? Okay. Okay. So L of 5 EI, it's going to be 30. Okay. So that's going to be minus L over 30 EI. Right? So you know from the Maxwell's theorem, so F21 is equal to F12, right? This is a theorem. And as well as our coordinate system and the entire system is symmetric, right? For this special case, So you can, if you want, you can just repeat the same step, right? You can just go ahead and apply a unit moment here and see the things are right. Sorry. See the things, what will actually happen, right? So that's going to be again like this, again like this. This is not occurring anything. So the same thing, it was a mirror image of this part. Was a mirror image of this, right? So mirror image of this. So here, can you see the here is going to be alpha dash. Here it's going to be alpha dash, right? So and it's going to push the beam. So 2L is on the force on the spring. Sorry, the force on the spring. So it's going to pull the spring, and the on the beam it will have a negative force, right? It will have a 2L force, right? It's similar. Now B and C has been swapped, right? That's it. So here in the beam you have 1 over L, and this, on the spring you have a force on the negative side, right? So it's alpha, and here it's you have beta, right? Beta dash, right? So here the relative rotation is 2 alpha. So you can see F22. So the displacement in the second direction due to the second coordinate, right? Due to the redundant at second coordinates, that's going to be 2 alpha dash minus that same alpha plus beta. If you draw it will be like this. It would look like this. Okay, the same thing, mirror image, right? So this is going to be alpha plus beta again. Okay, this is going to be alpha plus beta in the clockwise direction. So this is going to be how much? This is going to be gamma plus beta. This has moved in the anti-clockwise direction. Gamma plus beta in the negative direction, right? So the same thing happens again. So there's going to be alpha plus beta. So these alphas are not equal, different alphas. So from this case, since it is symmetric, the loading symmetric and everything symmetric, as well as the redundants are also symmetric. So F11 is equal to F22, right? It's going to be, so if you want, you can find like that, and you will ended up with 11L over 2LEI, right? Okay, so you can go ahead and write the displacement equation. So the displacement in the original structure is equal to displacement at that joint in the primary structure plus the flexibility coefficients into the force matrix. So your force is now bending moment B and C. Right here you saw at B and C relative rotation was 0. Why? The beam is continuous. After adding a hinge, you got a displacement, but the displacement was same, right? So I will write D1 and again D1. Why? The D1 with D2 was equal, right? And I got F11, F12, and F21 is equal to F12, right? You remember, for this case only. And finally, since this is symmetric, MB is also equal to MC, right? So I will write it here, D2. Since D1 equals to D2 and F11 is equal to F22, for this case only, I will write it as lambda. I will write this as F21 is equal to F12 is equal mu. Okay, I can write like this. Take this as D. So I will simplify this. F11 means lambda into MB. So I can write MB is equal to MC is equal to M naught. I would say lambda M naught plus mu M naught, right? So here it's going to be again mu M naught plus lambda M naught. So what can you say? Even though it looked like two linear equation, it is the same equation, right? So we don't need matrix inverse to find this, the same equation, right? First and two. So exactly one solution it has, right? So you can find it for M naught. M naught is equal to sorry, M naught is equal to D divided by, so M naught, when you take M naught out, you can write lambda plus mu, and it is equals to minus D, right? What was D? You remember? D was WL cube over 30 EI. So what is F11 plus F22? 11, this is 11 L over 2 EI, right? Yes, 2 EI plus minus L over 30 EI. So this is going to be 60 EI over how much? It's going to be 55 minus 253 L, right? So that's going to be 53 L not 60. So it's going to be cancelled 2. So your M naught is going to be minus, so this is MB and MC, going to be minus 2WL squared over 53, right? 53. L is getting cancelled, 1 L is getting cancelled. This is going to be L squared over, yes. So this is going to be how much? If you solve it, it would be 0.037 W L squared negative. So negative means it is acting actually in the anti-clockwise direction. So that means anti-clockwise direction, because we consider this half. So it is in the other way around for the next half, clockwise. Okay. So the bending moment we found, right? It's minus, so that is anti-clockwise moment, right? So now our second method, we need to cut the springs. So we don't have any springs, right? If we cut it, so that's going to be basically like this. That's it, right? So you cut the springs and B and C here. So it's just a simply supported beam. You do not have any connection with the springs. You just removed VB and VC, right? So we need to find now actions. Why? We need to find the MB and MC, right? Those are not now our redundants. Our redundants are RB and RC, right? Redundants. So we call them as first coordinate and the second redundant coordinate, right? So our actions, we will take actions coordinate. So here actions 1, action 2. So the required action is MB and MC, right? So those are the things need to be found. So our redundants are RB and RC. So since there are no any springs, this is just a simply supported beam, right? So we don't need any support settlements of springs and stuff, blah blah, right? So we don't need that bullshit. So we can just go ahead and find the things, right? So this is our primary structure. So if we cut this, okay, if we cut this, okay, this is our primary structure. Okay. So W intensity, the total length is 3L, right? So we need to find the deflection. So we are removing a force, right? We are removing a force. So that means we need to correspond with the shape. So how? By the linear displacement. If it is a moment, we need the rotation. If it is a force, for the linear force, we need the linear displacements, right? So we need to find this displacement. Right? So it is going to deflect. I would say this is D1 and D2. So both are equal, okay? Because this is also symmetric. Plus D, right? So how do I find D1 and D2? So that's simple, right? A, B, C, and D, right? So just remember this is L, and this is L. The total length is 3L. So I need to find the appendix, and so from the appendix, if it is loaded like this, right? If it is loaded like this, I need to find at the 1/3, right? At the 1/3. So at the 1/3, so you need to actually x distance, at the distance of x, the deflection has been given as f6, right? Can you see? So I need to find when x is equal to L and x is equal to 2L, right? And here, right? When it is L and when it is 2L. So probably both are equal, right? Because the shape is symmetric. So I will only find x equals L, and it is equal with x equal 2L, and the total length is 3L, right? But here the total length is L, so we have to be careful while using the appendix. So F6 is going to be this. So I can write Q is W, X is now my L. So EI not going to change, that's going to be 24 over EI. Okay. So my L is actually 3L. 2, L is actually 3L. L is actually 3L and X is L. X is L. So this is going to be 81. So this is going to be -6 plus 1, right? Is that right? So no, this is going to be 27. 27 plus 1, 28. So 28 minus, so that's going to be 22. W L to the power 4 over 24 EI. So this is going to be 11. This is going to be 12. So 11 WL4 over 12 EI, right? So for this, earlier I had only rotations, right? Sign convention. This I have the things in the other way around as well. So I will consider the clockwise positive and the rotations as well. And the forces in the upward directions are positive as well as the displacement. So D1 and D2 are in the negative directions, the downward direction. So those are negative, right? So that's going to be minus 11 W L4 over 20 12 EI. 11 WL4 over 12 EI. Now my D is okay. So I need to find what is the MB and NC, right? MB and NC. Do I need to find that? Yes. So how can I find? So this is just simply supported and what? Symmetric. So this is the total W is 3WL. So this is going to be 3WL over 2. This is going to be 3WL over 2. Right? So you can just cut it from here as exactly at B and take the bending moment. Okay. So I would consider it is clockwise. Okay. I don't know. Right. So I need the other part. Okay. I would consider this is okay, whatever. But my clockwise is positive. Okay. So this is the left heart. Okay. I'm solving for this, right? So usually I'm taking this one because that's convenient for me. Okay. If you want, you can do it. No problem with that. Okay. So okay, I will go with this location for this question. Since then you have no worries. Okay. So yes, I'm getting m is, so I can take bending moment about this point. So m is m plus 3wl over 2 into the length is L, right? Minus this is WL into the length is L by 2. It's equal to 0. So M is going to be minus 2 WL squared over 2, right? So that's going to be minus WL squared. Okay. M is going to be, so that's actually telling you what? M plus, clockwise is positive, and you have actually sagging bending moment, right? So that's what they are telling. So M is, so this is action. Okay. This is A, V, the primary structure, V, M, B, S, the primary structure, right, is equal to MCS here and here. So those are my actions, because my redundants are RB and RC, right? The problem has given to find has provided us to find MB and MC, so I need to take them as the actions. So my actions are going to be so since this is symmetric, my MB and MC are equal. Okay, whatever the hell happens. So my action of the primary structure is going to be minus W L squared. So this is my first action, second action. So I will consider this one, this part. Okay, not this. Okay, this is equal to both equal. Okay, and the opposite sign. Why the sigma m at 0? Sigma m at or any section is 0, right? So yes, this is primary structure, not the original structure. That's why. Okay. So now I'm going to apply the first redundant. So I remove the redundant. So now I'm applying a unit redundant. Unit force, right? So I need this. This is how much? This is the F11, right? And this is F21, simple F. Okay. This is also simple F. Flexibility coefficient at first redundant coordinate due to the applied redundant at first coordinate. flexibility coefficient at second redundant coordinate due to the applied redundant at first coordinate, right? That's how we read it. So we can see our second redundant, when we apply the second redundant, that's going to be like this, right? So the effect is, it's like symmetric, right? Now this is going to be F22. This is going to be, so the flexibility coefficient at second coordinate due to the force redundant at unit redundant at second coordinate. This is going to be flexibility in the first coordinate due to the redundant at second coordinate, right? So this is unit force, right? So you can see both these two should be equal. This is anyway equal. It is the theorem, but for this special case, this is equal, right? So we need to only find one of these, right? Actions as the same, actions is going to be the same, right? So need not to worry, right? So we can find this easily. And how we are going to find this is we can, yes, we can start it from the first one. Right, we apply a unit force, right? So we need F11 and F21, right? And yes, F11, F21. What's that going to be? So we need to find from the appendix here. Yes. So I can find from these, right? So L is the total length. Now my L is 3L and B is the load to, sorry, distance to load. Okay. And X is the distance to where I'm finding the deflection, right? So for the first case, right, it's like this. So I need this and I need this. To this, L is actually 3L, right? B is the load to the force, the distance to force is actually L, and the distance where you find the displacement is also L, right? But here, have a look at that. Have a look at that. So it says, right? So here X is equal or less than, right, B. And here X is greater than or equal to B. Here I think the equation is wrong, so you can't probably use this. You can't probably use this. I think printing mistake in this book, right? So you have to use from this, right? So, but either way, you can see if it is equal, okay? If it is equal, so in the both the equation, you can use for equal, X equals B, you can use it, right? Here you can't only use if your X is less than B, right? X is less than B, right? So for equal cases, you can use it. So here you can see B is equal with X, right? Here also not, here also not, right? Here you have to play the trick, right? So you can see if you use it, L is 3L L is 3L, and B is L, and X is what? 2L, right? X is 2L. Is that right? Yes. Is that right? Right? So L is 3L, the distance to load is L, and X is 2L. So X is larger than B. So you can find this for both cases. So you know this is going to be F11. So that is same as F22, right? So this is F21 and same as F22, F12. So, but I'm not going to hide, when you apply a load like this at the second coordinate, so your B is 2L, and when you find here, your X is going to be L, which means X is less than B. So you can use this, you can't use this equation. But how we are going to trick that? So in such case, if you know this theorem, you can take F12 equal to F21. But still, without that also, you can take it. How? Just take the mirror image of this. Just take the mirror image of this, right? Okay, mirror. And if you take the mirror image, what happens? You have to find delta here, right? So that's again similar thing as F21. That's okay. But that means you can use X from here now. So if you use X from here, right? So your X becomes what? 2L, and the distance to load is become, so this is the X, distance to load become B is equal to L. So now X is larger than B. So you can use that equation and find. X is measured from here. It's like this mirror image, right? Nothing happens. Even if you take it from this theorem, it is the same principle, right? Same thing, right? So you can find F1 from here. So it's going to be, I will take the snapshot. It's easy. So you can find F11, which is equal to F22 for this case only. Okay, this is not a universal theorem, but this is a universal theorem. Okay, F12 is equal to F21. Okay, this is not universal. So your P is, you are applying a unit load. So P is 1. Okay, P is 1 and B is L. So your L is actually 3L. 3L minus L means 2L. This is going to be 6. L is 3L. So that's going to be 18L EI. So 2L means again 3L. X is L. So that's going to be 2, 3L into L minus L squared minus B is also L squared, right? So that's going to be, so this part going to be 6 minus 2 is 4L squared. So altogether that's going to be how much? 6 minus 2 is going to be L, and that's going to be 4 into 8 over, so say it cancelled, 8L over 18 EI. So that's going to be how much? 4L over 9 EI. Is that right? Yes. Right, 4L over 9 EI. So that is, so we are considering positive displacements, right? So that is positive. So this is plus. Right? This is how much? We can write this. This is going to be, yes, I can find now. Okay. I can find this as F21 is equal to F12. So it's F12 as well. This is universal, okay? Okay, we are finding this. So P is 1, B is L. So L is 3L minus X is 2L. So again, find going to be 18 L into EI into, this is going to be again 2L is 3I. So that's going to be X2 3L into 2L into 2L squared minus B is also L squared. Okay. So this is going to be how much? L. So L squared over 18 LEI into how much? This is 2 into 2, 4, 4 into 3, 12. 12 minus, this is 4, this is 5. 2 to the power 2 is 4, 4 plus 1 is 5. So that's going to be 7L. Is that right? 12 minus 5 is 7, right? So that's going to be B is L, and yes, X is going to be 2L. So this is going to be how much? 7L squared over 18EI, right? So I hope it's correct. Okay. So 2 into 2 is 4, 12, 12 minus 5 is 7. So here it's L, 3L. So 80L over EI. It's going to be, yes, it's correct. 7L squared over 18EI. I think this is also should be L over L squared, because everything was L squared here, L squared here. L squared here, L squared, right? So here only L is at the denominator. So I think it should be L cube. L cube. This is also, I think, L cube should be. Right? L cube. So sorry about that. So I think it should be L cube. The way it seems, B is L. So here also you have L. So that means L squared. Here also you have L squared over L. So L to the power 4 over L. So that should be L cube. Okay. So this is equal to F22, and this is F12. So you can just find the MD and MC. So you just cut here and then cut here and equate it, right? So if this is 1, so you are using 1 unit load. So this is going to be how much? If you take bending moment about this point to the whole system, this R should be in, sorry, I will take, if you take bending moment about this point to the whole system, you know at the end bending moment is 0, right? So total bending moment also about the system is 0. So you can take just 1 into VA. So VA plus into 3L is plus 1 is 0. So VA is how much? Minus 1 over 3L. So you can just find MB as well. So if you cut here, MB is equal to MB plus, so you can take bending moment about this point. MB plus is minus 1 3 over L into L, right? VA is minus 1 over 3L. Is that right? This is 3L. No, 1 into, this is wrong. So the force into distance, this is 2L. So this is going to be 2/3. So it should be, because if you apply 1, so it is the nearest position. So that should have a larger load, and this should have a smaller load. So this implies you have the common sense, the importance of common sense you should have. Even if I simply did a mistake here, I noticed that there's something wrong, right? So just I can so this is going to be -2/L into L, and our 1 is not coming, right? One is exactly at the middle, at the below the point, so it's going to be 0, right? So MB actually. So this is the action, okay, action unit at first coordinate due to the redundant at first coordinate. MB is how much? 2L/3. Okay, 2L/3. So this is going to, so here if you take bending moments, you can determine it's going to be MC minus 2/L, 2/3 into 2L plus 1 into L, right? So that's going to be 4/L minus 4L/3 plus L, 3L/3, right? So it's going to be how much? Minus L/3, so that's going to be L/3, right? So MC, this is actually action unit at coordinate 2 due to the redundant at coordinate 2. That's what we are finding, right? So our actions. So we got force, so the delta for the displacement, sorry, force equation. So T is going to be flexibility into force, right? So this was also a similar case, right, where you would end up with exactly one equation, right? Why the system is symmetric and the actions and the redundance we are finding is symmetric, right? Is exactly not about the system but the redundance. If the redundances are symmetric, so we can take this. So redundancies are symmetric due to the system is symmetric. Okay, those have a relation, right? So I can just write one equation for in, so that, so delta, so I will hold this delta, okay, for now. So D was how much? D was 11 WLs L4 over 2LEI. And F12 was 4L cube over 9EI, 4L cube over 9EI. 9 EI. 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 9 I into, I will call this F1. So F1 is basically MD, okay? That is same as MC. That's why we don't need second equation, right? We can just plug and see everything from the first equation, only one equation. So this is going to be 18 EI. Okay. So now I find 18.8. So my delta is going to be how much? Okay. What is delta? That's the question. So the original structure, right? So it has some settlement, right? It settles like this. So what is this delta? But you know the force is F1, right? Sorry, the force was not MB. Force was not MB. Sorry. This is not MB actually. This is RB and RC, right? So what is this force actually? So it's a trick, right? So if you notice delta, so let's call this delta. What is delta? And so you know the force, right? That's what you are finding. So you have delta. What is that? F equals F1 equals K into delta. So you can write the displacement in terms of K. So that's going to be F1 over K, right? So I can just go and plug it in here. To be, it's pretty easy, right? Nothing difficult, it's common sense. Okay, right? So I can solve this because this is 18 over 8, right? So this is going to be how much? So this is F1. So K was 20 EI over L cube, right? And minus W L4 I going to be 15 L squared F1 over 18 EI. So for both these two, the common denominator is, so I need to reduce that. So I need to bring it here and the other one the other way around. So 11 W L4 over 12 EI is going to be, I can take 180, right? So 15, I can take F1. So that's going to be 180. So for 180, 20 or 9, okay? You have 9. And for 180, 18 into 10, right? So you have 10, 150 minus how much? Here you have 20 into 9, right? Is that right? So 15 minus this one, right? So for 180 you have 18 into 10, so that's going to be 150. So for 20 it's going to be 9, so it's going to be 150 minus 9. So f1 is going to be how much? 11. So you have altogether L cube over EI. So EI is getting cancelled, L is getting cancelled, right? It's going to be 11 into 180 divided by 141. Okay, divided by 12. Okay, so that's going to be 0.17 WL, right? 0.17 WL. So soon I got that. I don't need to even use the action matrix since I know the reactions, or else okay, you will use it, otherwise it will get confused. So from the Fonts equation, actions is equal to actions of the secondary structure, primary structure, and action unit matrix into F. So this is also not two equations, this is also just one equation. All you need to find is MB, right? So you remember A is the primary structure, it was WL squared, so you can take only one, plus action unit was 2L over 3 and L over 3, right? 2L over 3 and L over 3, right? That's going to be okay. 2L over 3 F1 plus L over 3 F1. So that's going to be F1, right? So if you reduce that, right? So I think we have find here a mistake. So that is yes, it's delta, right? So this delta is occurring in actually the negative direction, right? We got upward positive, right? So here you should be negative, right? So that means it is going to be positive. So that's going to be how much? 180 into 11 divided by 12 into 159, right? So that's going to be so that's going to be 1.0377 WL squared, right? So here also That's going to be F1. So F1 is 1.0377 WL squared. So finally, I'm getting its WL squared. I can take it out. So that's going to be 1.3 minus 0. Okay, minus 0.037. So that's going to be 0.037 into WL squared. So this is now positive, right? So you remember 0.0377 WL squared. You remember from this also we found minus 0.077, right? So why is that? Because the first one was done actually considering this half, and we ended up with negative value y, that is actually anti-clockwise, right? For the second half, right, when the spring forces are redundant, we choose this one and we ended up with positive, right? So exactly same, we ended up with the clockwise moment. So it is balanced, right? So MB was equal at the each case, right? So it's here and it's here. Sorry, not F1 here. It's an action here, okay? So here it's going to be one step, okay? So this happens actually A is equal to actually now our actions are MB and MC, right? So and the actions in the primary structure were, you remember, WL squared over WL squared. So you remember the coefficients. 1 was 2 over 3, right? 2L over 3. This was L over 3. You remember this was also L over 3 and this was 2L over 3, right? So this was F1 and F2, right? So again, what happens is these two are equal. These two are equal. So what happens is this become a one equation. MB is equal to minus WL squared plus 2L to the 2L into F1 plus L over 3 into F1. So it's 2/3 plus 1/3 into F1 because F1 is equal to F2. So that's going to be just F1. So this is going to be minus WL squared, right? This is going to be either MB or MC. So this is MB, right? So you can find from this. Thank you.